Over to you, Songqi.
Thank you for having me here today. Today I'm going to talk about the stable parametrized h-cobordism theorem. And this talk can be divided into 3 parts. In the first part, I will introduce to you the main players of this theorem today, which are the space of h-cobordisms, the Whitehead space or the Whitehead torsion, which is the classical definition, and the Waldhausen A-theory space. In the second part, I will sketch a proof of Waldhausen's stable parametrized h-cobordism theorem in the smooth case. And finally, in the third section, I will describe how to generalize it to the case of smooth manifolds with tangential structures. And here comes the first player, which is the h-cobordism. In this section, CAT stands for topological manifolds or PL manifolds or smooth manifolds. And the main purpose of this project is to extend the theorem to the case of smooth manifolds with tangential structures. So first, we recall the definition of an h-cobordism and a cobordism. Let X be a d-dimensional manifold, possibly with boundary. Then a cobordism W on X is a d+1 dimensional manifold, whose boundary is the union of X with another manifold along their boundaries, as shown below. And a cobordism is an h-cobordism if both the inclusions from X and Y into W are homotopy equivalences. And it's worth noting this important theorem by Milner, Smale, and Morlet, and some other people. For a closed manifold of dimension greater than or equal to 5, if it is simply connected, then every h-cobordism on X is isomorphic to the product of X with the interval. So why are h-cobordisms important? Because generally classifying manifolds up to homotopy equivalences or up to isomorphisms are very hard, which is why weaker classifications than isomorphisms are studied. For example, h-cobordisms. H-cobordisms are interesting because it is not only computable, but also non-trivial. There are cases where it is even more subtle than the characteristic classes. For example, there are fake length spaces that are h-cobordant to the dense space, but they have the same stable Whitney class or Pontryagin class with the classical length space. But to investigate the case where X has non-trivial fundamental groups brings out the second player today, which is the Whitehead torsion. So let's first see some relation of the Whitehead torsion with the other concepts in literature. So first, the Whitehead torsion is a generalization of the Riedmeister torsion. The Riedmeister torsion is also important because it is with that we first classify the 3-dimensional length spaces. And second, the Whitehead torsion is an obstruction to a homotopy equivalence, being a simple homotopy equivalence. And recall that a simple homotopy equivalence is just a map homotopic to a finite composition of the following operations. The first one is filling a horn, and the second one is collapsing one. Just as shown in the following picture, the arrow on from the left to the right is filling a horn, and in the other direction is collapsing one. So then we record the definition of the Whitehead group. It's an algebraic definition. Let G be a discrete group, then the Whitehead group of G is by definition the quotient of the first K group of the group ring, K1 of that G by the group generated by plus or minus 1 and G. Equivalently, you can also define the Whitehead group as the quotient of G of that G modulo the subgroup generated by E plus or minus 1 and G. Here, E stands for the subgroup generated by the elementary matrices. So here are some examples. The Whitehead group of the integer is trivial because every Laurent polynomial is invertible if and only if it's plus or minus 1. And however, there are some cases where the Whitehead group is non-trivial, for example, Z mod 5Z. Here we have a non-trivial unit, which is 1 minus t squared minus t cubed. You can check that it has an inverse. And then we transfer to the field of topology. So to every homotopy equivalence, there's a way of assigning it an element in the Whitehead group. With that, we are prepared to state the h-cobordism theorem. Here, S stands for the simple homotopy equivalence. For a manifold, no matter the topological manifold or PL or smooth manifold of dimension greater than or equal to 5, an h-cobordism on X is trivial if and only if the Whitehead torsion of the inclusion is trivial. Or equivalently, this can be said that the inclusion is not only a homotopy equivalence, but a simple homotopy equivalence. We know that with surgery, every element of the Whitehead group can be realized as the Whitehead torsion of an h-cobordism. That said, that the map from the connected component of the space Whitehead group is surjective, or yes, it is surjective, and the h-cobordism theorem says that the kernel of this map is trivial. So here is the definition of the h-cobordism space. Although it seems a digression to just define this moduli space of h-cobordisms, but we will see it's important later. The h-cobordism space on a manifold X is by definition the simplicial set Hx, in which an n-simplex is a bundle over the standard n-simplex delta n, satisfying the following conditions. So first, it has a trivial subbundle X times delta n, and the second one is that its fiber over every point is an h-cobordism on X. And this X is the fiber of that trivial bundle at this point. And as being said, that the connected components of Hx is there's a map from the connected component of Hx to the Whitehead group. But then what can be said about the higher homotopy groups of this h-cobordism space? And how is this related to some higher analog of the Whitehead group? That, in fact, there is a Whitehead space functor WH, which is compatible with the classical definition we've seen before of the Whitehead torsion in the following sense, which is the fundamental group of the Whitehead space is isomorphic to the Whitehead group of the fundamental group X. However, unexpectedly, from n greater than or equal to 2, the higher homotopy groups of the Whitehead space depend on the entire homotopy type of X rather than just the n truncation of X. If we look at this problem from an algebraic point of view, this amounts to finding the correct kernel. We've seen in the previous slides that the Whitehead group is the quotient group of the general linear group with respect to the subgroup generated by the elementary matrices plus or minus 1, and the diagonal matrices generated by the group itself. And if we identify this group ring Z pi 1 of X as the pi naught of the ring spectrum as loop X, and identify this X here as loop X, and pi 1x as pi naught of loop X, then this question reduces to find the correct or the most appropriate generalization of this missing term in this vibration sequence. And an easy step is to identify the plus construction for BGL as a generalization of GL multi B, because in the discrete case, GL multi B can be identified as the plus construction. But then there's something left, which is the subgroup of units generated by plus or minus 1 energy. So it's very hard to find the correct generalization, and in fact, it is out of the genius of Waldhausen to make the appropriate generalization, which brings out the final player today, which is the Waldhausen A-theory. It can either be a topological space of the homotopy type of a CW complex, or just a syntetical set. A retractive space over X is a space over X with a section, namely just from X to Y to X. A space over X is from Y to X, and the section means the composition is the identity. The A-theory space of X is the K-theory space of the category of finite retractive spaces over X. So here, the weak equivalence in this category is defined to be weak homotopy equivalences. I'm not going to write down explicitly how the Waldhausen defined his K-theory space. So all I'm going to say is that the functor K is a machine that takes a category of with compatible co-vibrations and weak equivalences as input and yields a space or a spectrum as output. On the other hand, the A-theory space can also be identified as the K-theory of the ring spectrum. We've seen that the A-theory space is the K-theory space of the category of retractive spaces over X. There's a variant definition of this, which will use the finite dominated space, retractive space instead. You shouldn't be worried about that. But then finite dominated retractive spaces corresponding to compact objects in this S stands for the infinity category of spaces. /X means it is the category of spaces over X. And here star stands for pointed, because our spaces over X are a pointed spaces over X means, so the point here in the spaces over X is the identity map, and pointed means there's a map to X. So this, and here the upper circle stands for the subcategory of vibrant covibrant objects. With strict mean, there's a categorical equivalence between spaces over X with the functors on X, or the category of diagrams on X, that with values in pointed spaces. And we know that the functor K is an additive functor, which means taking colimit with respect to suspension gives us a homotopy equivalent K-theory space, which gives us the third homotopy equivalence, because taking colimit with respect to suspension makes this pointed space into a spectrum. And on the other hand, we can identify the category of diagrams on X with values in spectrum as a local system on X with spectrum value. But this is equivalent to giving a spectrum and then give it a loop-X action, which is equivalent to an S omega X model. And this perfect is equivalent to the compact definition. And then you are free to use your favorite model for a K-theory of a ring that can be generalized to the K-theory of a ring spectrum to define the A-theory space. The difference between A-theory and a homology theory, or a general an approximation of A-theory by a homology theory is given by the adaptive map. It is an excisive approximation from the left. Waldhausen used his vibration theorem to show that there's a vibration sequence, which we are going to use as the definition of the Whitehead space. As you see, the loop of the Whitehead space is the homotopy fiber of this map alpha, defined just by using homotopy theoretical methods. So now we have the answer for our previous question. We have the missing term because Waldhausen computed that AX is homotopy equivalent to Z times BGL S loop X plus. And then so if you remember that previously, the missing term, if we add plus there, it would be, and then the missing term, so E is modded out because we take the plus construction. So the missing term would be, the missing term would be this homology theory with coefficient spectrum dA of a point. And here, WH is short for the PL Whitehead space. And then we are going to look at Whitehead space in some different other settings, namely the smooth setting. So by definition, the smooth Whitehead spectrum is the homotopy co-fiber of this map, where this map is the composition of the following two maps, where the second one is the adaptive map as before, and the first one is induced by the unit map, just from the sphere spectrum to A of a point. And we know as a fact that I should say that the smooth Whitehead space is important because it is an obstruction in the parametrized case to a map being homotopic to a diffeomorphism. Namely, given a manifold bundle, we are able to define a map from the base to the smooth Whitehead space of the total space. And this map being now homotopic is an obstruction to this bundle to be fiber homotopic to it. So suppose we have a bundle map to E prime. So we have a torsion, and this torsion is now homotopic even if this torsion is not now homotopic, then this bundle map cannot be homotopic to a bundle diffeomorphism. Ground section. And now I will just sketch a proof of Waldhausen's stable parametrized h-cobordism theorem in smooth case. So we first state the theorem. Recall that the stable h-cobordism space is just the stabilization of the h-cobordism space with respect to dimension, namely just taking the colimit with respect to the dimension, the stabilization map, which is just from hx to hx times the interval, and which is rather simple. And the following theorem connects the stable h-cobordism space to the Whitehead space due to Waldhausen. Let X be a manifold of dimension greater than or equal to 5, then the stable h-cobordism space is homotopy equivalent to the loop space of the Whitehead space. So this holds in the category of topological manifolds or PL manifolds or smooth manifolds. So first we make a few remarks on the theorem. As said before, taking connective components of both sides reduces to the h-cobordism theorem. And this theorem can also serve as a definition of the Whitehead space. You cannot just define the Whitehead space as the de-looping of the stable h-cobordism space. And if this is the case, then you need to prove the following homotopy fiber sequence, which we use as the definition. And in fact, the PL case is the most difficult, which requires a complicated study on the simple homotopy equivalence between polyhedrons and the space of retractive spaces, and also simple homotopy equivalence between retractive spaces. And the topological case can be reduced to the PL case just by passing to the stable normal disk bundle by the Whitney embedding. We can just embed every topological manifold into the Euclidean space, and then we take the disk bundle of the normal bundle. It is always a PL manifold. By pulling back to this normal disk bundle, we reduce it to the PL case. And in the following, I will sketch Waldhausen's proof of the smooth case by just a comparison to the homotopy fiber sequence in the topological case. So we need to make a digression first, which is we record the good-Wheeler calculus. For a space or spectrum valued functor on spaces, there's a natural universal right excisive approximation denoted by Fs. So all we need to know about it are the following facts. The first one is that the excisive approximation of a homology theory is itself. And the second one is a statement by the excisive approximation of this stable smooth h-cobordism space is trivial. Here D stands for smooth. And now we are prepared to sketch the proof of Waldhausen's stable parametrized h-cobordism theorem in smooth case. So by the fact on the previous slides, we know that HD is homotopy equivalent to the homotopy fiber from HD to this natural map, because this term is contractible. And by more or less smoothing theory, we know that the homotopy fiber of this forgetful functor from the smooth h-cobordism space to the topological one is a homology theory. This functor is simply just forgetting the smooth structure, which give us the second homotopy equivalence, because if we have a homology theory as the homotopy fiber, then we take the excisive approximation. We know this is going to be itself because it is a homology theory. So we know the homotopy fiber are homotopy equivalent. So this gives us the second homotopy equivalence. And the third one is obtained by just applying this excisive approximation to the theorem in topological case, which says that the HT to some homology theory, and to A is a vibration. So we take excisive approximation. This is itself to A of S. So we know the homotopy fiber is the loop of the homotopy fiber of the third term, because this term is contractible. The last ingredient for this proof is this fact that the composition of the map from the stable homotopy theory to A theory, and then to the excessive approximation as a homotopy equivalence. This can be proved by you can either use Waldhausen's original proof or just see it by some computation on the topological cyclic homology. But we just take it as a fact. So given always a homotopy fiber sequence relating the three homotopy fibers, namely the homotopy fiber of the first map, the homotopy fiber of the second, and the homotopy fiber of the composite. We know that this fits into a fibration, and since the composite is a homotopy equivalence, we know the homotopy fiber of it is contractible, which means the first term is homotopy equivalent to the loop of the third one. So we conclude that the stable parametrized h-cobordism space in this case is homotopy equivalent to the loop of this fiber, and to that, and then by definition, that's the loop of the Whitehead space, and that's finished the proof. And then I will describe how to generalize this to the case of smooth manifolds with tangential structures. So first we look at the definition, or we record the definition of tangential structures. A tangential structure, theta, is a collection of spaces, theta D, and theta D is equipped with an OD action, and these actions should be compatible with each other. And a theta structure on a vector bundle of rank n is an O(n) equivariant map from the frame bundle to theta n. Or equivalently, you can write it as a section of the associated fiber bundle of the frame bundle with whose fiber is theta n. And a theta structure on X on a manifold is a theta structure on its tangent bundle. These are just routine definitions. So we make a notation, which is that theta X denotes the space of theta structures on X. And here are some examples. When all of theta D takes a constant value of that mod 2, that gives us the order. D takes OD, then a section is just a trivialization of the frame bundle, which is an unstable frame. And when theta D equals to the stable orthogonal group, which is O, then that is equivalent to a stable frame. And of course, there's the case where theta D is equipped with the trivial action. Here, when theta D takes a constant space, which is constant with respect to D, and this space is equipped with the trivial action, then a tangential structure in this case is a homotopy class of maps from X to N. And we make a definition of the space of h-cobordisms with tangential structures, which is similar to Waldhausen's definition. The h-cobordism space on a manifold with theta structure is by definition a central set in which an n-simplex is a bundle of h-cobordisms on X with compatible theta structures. So at each point in delta n, its fiber is an h-cobordism on X equipped with a theta structure that is compatible with the theta structure on X. And as before, there's a forgetful functor from the space of h-cobordisms with theta structure to the space of smooth h-cobordisms just by forgetting the theta structure. And then we meet this definition of group of automorphisms of smooth manifolds with theta structures. As we are going to see that this is a homotopy theoretical definition, let X be a closed smooth manifold with theta structure. Well, this definition can be generalized to the case with boundaries where we have just a compact smooth manifold. Just for simplicity, we only focus on the closed case, the simplicial set of automorphisms of structure up to preferred homotopy is by definition the homotopy fiber of this map. This map EB, this map sends a diffeomorphism to the induced theta structure. Every diffeomorphism induced a theta structure from the given one. And we define the automorphism group as the homotopy fiber of this map. And we know that this is actually a group like H space, so you can just safely just think of it as a simplicial group. And we let this notation to denote the homotopy fiber from O(n) to theta n. This is just a notation. These automorphism groups determines a spectrum just given by taking the homotopy quotient of the d+1 dimensional automorphism groups to the d-dimensional automorphism groups. And it comes with a natural map to the sphere spectrum just by because the homotopy fiber definitely have a map to O(n), and O(n) plus the quotient of O(n) plus 1 over O(n) is Sn, which give us the sphere spectrum. The Whitehead space is then defined to be the homotopy cofiber of this map of spectrum. And here again, we have this map as the composition as from into the stable homotopy theory, and that map is what we use to define the smooth Whitehead space. And here we can compute the space of theta structures, or at least stably. Let X be a compact smooth manifold with a theta structure, then the stable space of theta structures is a homology theory, whose coefficient spectrum is given as follows. Of course, we need to make some assumptions to make this actually a spectrum. You cannot just arbitrarily choose theta d and expect that this forms a spectrum. And we know that this is a homology theory, which is important, as we are going to see just in a minute. As before, the stable means taking colimit with respect to dimension, which is usually theta x to theta x times r, and going on. And this statement can be proved either by, similarly to the topological case, by pulling back to the unit normal disk bundle, which will then becomes parallelizable. It would be much easier to compute the space of tangential structures if you just have a parallelizable manifold stabilize. Or we can prove it, but just use a homotopy theoretical methods, which is a generalized statement of punctuativity. And then comes our main theorem, which is the generalization of the stable parametrized h-cobordism theorem for this case of smooth manifolds with tangential structures. Let X be a smooth manifold with tangent theta structure. I'm sorry, of course, I need the assumption that the dimension of X is greater than or equal to 5. Because I obtain this result by comparing to the smooth case. Then the stable h-cobordism space on X is homotopy equivalent to the loop space of the Whitehead space in this case, which takes a similar form, just the exact same form as Waldhausen's theorem. And we also know that the forgetful functor, the vibration induced by the forgetful functor splits. And this splitting actually provides a way of understanding the splitting of A-theory, as we are going to see in the next slides. Sorry. So in this example, we see that when we take the tangential structure as the unstable framing, then what we have is the following, which means the A-theory space is homotopy equivalent to the Whitehead space in this case. And we have the splitting from the Whitehead unstable framing to the smooth Whitehead space. We know that this splits is a homology theory, so it splits which provides a way of understanding the splitting of A into the smooth Whitehead space and the stable homotopy theory, which is a result by Waldhausen. We just identify it as just by forgetting the framing. And that's all for today. I'm sorry I finished a bit early. Thank you for your attention. And here are the references.
Thank you very much, Songqi. Are there any questions?
I just have one. At the start, you mentioned that like these h-cobordisms, classification up to h-cobordism kind of sits between various levels of classification. What kind of is the reason that you care about having this intermediary step? Like, what features do they capture?
Because when we cannot do something, we just take a step back and try to do something that is easier. But although it doesn't give us as good as the thing we actually want. For example, in this case, we want to classify manifold up to isomorphisms, but that is almost impossible. So we just turn to a weaker one, weaker classification, which is up to, there are a lot of classifications, but h-cobordisms is only one of them. And it is I wrote there. And there are cases, or in some cases, it is actually as good as what we want. For example, if two length spaces are h-cobordism, then they are actually isomorphic, which means if we are restricted to the only spaces that are only the length spaces, then classification up to h-cobordism is the same as classification up to diffeomorphism.
Okay, cool. Thanks so much.
Are there any other questions for Songqi?
I had one question. So you stated two theorems, and in the first one, I think you indicated that you need some hypotheses for that thing to actually be a homology theory.
Yeah.
And so is it correct that the same hypotheses would need to be imposed for the second theorem as well?
Yes, thank you for pointing that out. And yes, in order to have this splitting of this vibration sequence, we need the fact that the space of tangential structures is a homology theory, and which we cannot prove unless making some additional hypothesis on that.
Great. If there aren't any more questions, then let's thank the speaker again. And with that, I'll stop the recording.